Now, this is dealing with the faint young sun problem, and I want to mention this briefly. We know that in the past, the sun was less bright than it is today. In fact, the solar luminosity measured over here on the y-axis, that's actually is reflecting of the decrease in the sun. For example, 0.8 on there means that back when it was 0.8, which was about 2.5 billion years ago, the sun was only giving about 85% of luminosity compared to what it is today. So that's what's meant by those numbers on the y-axis. So you can see that back 4.5 billion years ago or so, the sun was giving off less than 75% of the amount of luminosity that it does today. Why is that? Well, we've talked about fusion before. When hydrogen is fused to helium, it creates more density in the center of the sun, and you have then more collapsing of the hydrogen and more fusing to create helium, increasing the temperature of the sun. And that's been taking place for the last 4.5 billion years, and it will continue to do so in the future. Now, some people have suggested, not any scientists, but some people have suggested that the variations that we're seeing in temperature today are due to a radiance increase by the sun. That's just not true. We can extrapolate this out, and we can see that it would take millions of years for this to have an effect on the Earth. You could talk about the sunspot cycles, but they're minor, and I'll show you a graph a little later on about how the sunspots are not affecting us. Very little impact from the variations we see from sunspot activity on the sun. So the reason I bring this up is that if we extrapolate back the gases, the greenhouse gases that we have today, let's take a look at this diagram. If we extrapolate them, you can see here the current carbon dioxide and water concentrations in our atmosphere, these greenhouse gases, the major greenhouse gases. If we extrapolate them back to 4.5 billion years ago, we go below the freezing point of seawater. So we would basically freeze the entire Earth back 4.5 billion years ago. But we have evidence that the Earth, for example, 2.5 billion years ago to 4 billion years was not frozen. We know about snowball Earth, but most of the time the planet has not been frozen. We have examples from, and let me just give you some of these, sedimentation by rivers, by streams. We have mud cracks, raindrop prints, ripple marks, sand dunes. We even have some glaciation, small glaciation. We have limestones, which we know were formed in warm water. So all of this comes to tell us that the Earth was not frozen because we have rocks with examples of this material in them that are that old. So we know that it was much warmer on Earth 4.5 billion years ago. And as we already know, the atmosphere that far back was very different than it is today. It had greenhouse gases in it. It had ammonia and methane and water and carbon dioxide in it, hydrogen sulfide, as you see by that red curve. So if we add those greenhouse gases, we can increase the temperature of the Earth so that we have a planet, much different atmosphere than it is today, but a planet that was warm, much warmer even than it was today, as you may remember from the first slide I showed you. Well, this is a graph of carbon dioxide in the past, the last 400 million years, in ppm. And we've done estimations by various procedures, and then we've taken some models and extrapolated what the carbon dioxide could be in range in the past, and that's by the shaded area, greenish shaded area there. And you can see that most of the calculations show or fall within that range. And so one of the things that I strongly emphasize here is that carbon dioxide was very, very high in the past. And today, I mean, look at that, we're talking about thousands of ppm, except for this interval about 300 billion years ago, and between, say, 30 to 40 million years ago, when we had glaciation on the planet like we do today, we had very high carbon dioxide. The problem with high carbon dioxide is that the oceans were 216 feet higher back then than they are today. So the glaciers keep us from having high sea level and more land. And so we should be worried about increase of carbon dioxide because we can flood out our cities along the coast. That won't happen in this century probably, but we have to be concerned, I think, now about this rather than in the future when it might be too late. This is a graph, kind of an interesting graph from experimentation. The people that did this work, they put calcium carbonate, critters that grow calcium carbonate, in seawater at different temperatures, and then they measured the oxygen, the O18-O16 ratio. Now, we talked about isotopes before, so this shouldn't be surprising. I put how they calculate per mil. We measure things in delta per mil, and it's just a fancy way, really, of expressing the oxygen 18 to oxygen 16 ratios. And what we have down here on the x-axis is the amount of O18-O16 ratio in the calcium carbonate that precipitates out, and the amount in the water. And then over here on the y-axis we have the change in degrees C temperature-wise. And as you can see, there's a nice correlation. And what's happening here is that O18 tends to vibrate at any given temperature less than O16. And so at lower temperatures, O18 is going to go into calcium carbonate a lot easier than O16. And then as the temperatures get higher and higher, the O18, O16 start to behave a little bit more alike, and you start getting less and less O18 taken up by the calcium carbonate, so as you raise temperature. So the great thing about this study is that it shows that if we measure the oxygen O18, I should say oxygen 18 and oxygen 16 ratio in shells, we can estimate the temperature in the past. And indeed, we've been able to do that with this particular graph. Notice on the x-axis over on the right side, we have an ice-free temperature. Now that's important. It has to be ice-free. As you know already, oxygen 18 is affected by the formation of glaciation. But it's good we can use the O18 to give us temperature if there are no glaciers out there. And so as the O18 goes down, the increase of temperature, as you saw in the last diagram. But then, and then that's between 65, 70 million years ago to around 40 million years ago. But when we start to have glaciation, we have to start considering the effects of glaciation on the O18-O16 ratio. Now, think about this. O16 is lighter than O18, so it is preferentially evaporated from the oceans and goes into the atmosphere. And therefore, when it rains over or snows where there are glaciers, those glaciers are going to be enriched in O16. So as the glaciers grow, they're going to include more and more O16 relative to O18, and they're going to enrich the oceans in O18. And so we should see a constant decrease in O18 as the glaciers get bigger and bigger. And in fact, that's what we see in this diagram. Notice that the O18 in the oceans is getting greater and greater as you proceed towards the present and the glaciation increased. So we can predict then from the extent of glaciation, approximately what the temperatures were then, and get an idea from that glaciation the impact of not only the planet from the effect of ice, but also the temperature. So O18 is a proxy, the ratio of O18 to O16 is a proxy for temperatures. And this data comes from what we call forams, which are little tiny tests or shells that we find in cores that are drilled by the deep sea drilling project. This is a graph based on del O18. It's taken, it's from sediment cores, and we can get the del O18 from these benthic forams, and we can estimate the temperature by the forams, by their O18, O16 ratios. And a couple of things become very clear. Over the last 3 million years, you can see all how temperature has gone down as we have approached the present based on the O18 ratios. First of all, we can say that ice volume has been increasing. We can say that the temperature has in general been decreasing. And third, we can say that it is much more cyclical. There's a greater variation between the highs and the lows towards the present. I think this is a very important graph. It shows this general trend towards cooling. And this maps Milankovitch cycles quite nicely. So we can blame those variations on Milankovitch and the amount of energy brought into the planet. But we still have to remember that even though temperatures have gone down, the ice has kept the oceans from rising to where we couldn't have cities where we have them today, like here in Florida, where I am. It's not going to take much of a rise in sea level to put most of Florida underwater. In fact, there's some predictions I'm seeing where Florida could be underwater by the end of this century. Again, I'm not trying to scare anybody. I'm just trying to explain that global warming is a very serious problem, and we should not be taken in by all of these false arguments that being spread, the anti-science articles that have been spread by the energy industry, as I mentioned when we started. Well, let's go to the next graph. This is similar. It's measuring the amount of, well, it's measuring the temperature from the cores, and it's also measuring gas from the Vostok ice core, carbon dioxide, we can get that, and the dust in there. And as you can see, these map Milankovitch cycles quite nicely too from the ice cores. The dust increases probably right before or just as the climate is getting hotter, and that's probably due to the beginnings of desertification. Well, the thing to point to is look at the carbon dioxide rising. I'm going to try to show you some information later on that suggests that carbon dioxide is rising because, or it should be delayed. That is, the carbon dioxide rising now may have a delayed effect on the temperature. We have some evidence that that's true, and I'll show you that later on. So we're seeing carbon dioxide increase even drastically, even though we're not seeing any temperature increases most recently on this kind of, well, we're seeing small temperature increases, nothing that we would expect from the carbon dioxide. So we're not seeing quite the temperature increase. I'll explain why that is, probably because the oceans are absorbing a lot of the temperature that would have gone into the atmosphere. So even though CO2 is going through the ceiling, we haven't quite gotten to the temperature increases in the atmosphere, again, probably because the oceans are buffering it. Well, take a look at this graph, kind of a blow-up here of the last 22,000 years. This is when the glacier maximum was, about 17,000, 18,000 years ago. Carbon dioxide's plotted on the y-axis along with a global temperature based on a particular average over 6.5 to 11.5 thousand years ago. And the first thing to look at is the yellow dots. Those are carbon dioxide taken from the ice measurements directly, and then temperature calculated from those ice cores in the red there. And then the blue is temperature calculated by other means, and you can see there's a delay there. As we have this tremendous rise in temperature and carbon dioxide, the blue temperature is being offset. There's probably a delay. So if we're seeing this delay back then, we're going to probably see it today. So the carbon dioxide that we're putting into the atmosphere right now is probably not being felt temperature-wise, and will not be felt at full force until probably towards the end of this century. I do want to emphasize, too, that look at the extent of the glaciation 17,000 years ago, the amount of CO2 that went into the atmosphere, and the melting that took place in the glaciers over that period of time. Now, things have stabilized over the last 10,000 years or so, but this is after we had 410 feet of sea level rise over the period from about 18,000 years ago to 12,000 years ago. That's well, even lower, 11 to 10,000 years ago. What would happen today if all of the ice melted? Well, we would have instant rise in sea level of 216 feet. That's an astonishing amount of water. Almost all of Florida, only little islands would not be covered by water in Florida. So we're talking about an immense increase. I don't mean to suggest that we're going to melt all the glaciers anytime in this century. There's a small chance of it, but it's a very slight chance. I think, though, that we have to get control of the carbon dioxide. As you'll see here in a minute, we are seeing the effects of this carbon dioxide on glaciers around the world, and we should not take this lightly. Well, here's some data over the same period of time on sea level rise. All of the things that have been used to measure the sea level rise are listed on the right there. Terraces primarily. And the sea level change has been significant. I mentioned it just a minute ago. About 125 meters increase to things flattening out, and we've had relatively stable sea level for the last 7,000 or 8,000 years. And that is changing. We're already seeing sea level rise, and we can see in just a minute how much the sea level has changed. But let's talk about the temperature of the oceans, because this gives us an understanding about why sea level is rising, or partly. This is a plot of global ocean temperature anomalies, and you can see that if we graph this, that in the early part of this century, global temperature was decreasing in the oceans, but it has been increasing ever since, say, about the 1970s or so, just about the time that we started seeing an increase in the atmosphere. And it's been going up ever since. 2015, we have the hottest global temperatures ever recorded on the surface of the oceans. So it's having an effect. Now, what we think is happening is that the carbon dioxide is being sucked up a lot by the oceans, so that we're seeing the warming of the oceans and less warming in the atmosphere to the extent that it should be. But eventually the oceans are not going to be a buffer for us, and we're going to see the impact on the atmosphere. This is probably why we have the delays that I was talking about in the previous diagram. This is another graph of a temperature, again, over period of time from 1880 to 2020 to give you, we didn't have as good a method of measuring temperatures in the past, so the gray area there is the uncertainty. But certainly we were down around a -5 in the 1800s, maybe even a lower, and this is in degrees Fahrenheit, and we've risen consistently since the early part of the 1900s, and it's getting serious. I've got some numbers here. We have oceans rising 0.74 degrees centigrade over the average of the 20th century. So we are having warming of the oceans. And what happens when you warm the oceans, you tend to expand water. And that, along with the intense melting of alpine glaciation, has caused the sea level to rise.